So, thank you very much for this introduction, and welcome to our webinar, Troubleshooting in Titration, also on behalf of Metro. The major focus of this presentation will be on how to proceed with any titration issue and should give you a step-by-step guideline to find the reason for your individual titration problem. So, does your titrator produce wrong results? Is it far away from where you expected, or is it changing slowly with time? Do your titrations only have a poor reproducibility, means you get different results for identical samples, or when different users are doing the same application? Or do you get no suitable titration curve at all, means you cannot find an equivalence point? Where to look first when the titration result is not what it should be? What very often is not thought of is that troubleshooting already starts before the start button at the titrator is pressed, means when you prepare your instrument. A titrator usually is ready to use, means the burette is equipped with titrant, the method is programmed, and the electrode is already connected to the measuring interface. The only major activity that is done before the titration is the preparation of the electrode. The electrode, therefore, is taken out of the storage vessel and then mounted in the titration holder together with the burette tip. But it already starts here. Is this done always exactly the same way? Is there a picture or drawing on how it should be? Important is that the burette tip is placed behind the electrode, considering the rotation direction of the stirrer. Otherwise, the titrant would be directly dosed onto the electrode, which may give wrong results. Is the electrode still filled with enough electrolyte, and is the refilling plug opened? If the level of electrolyte in the electrode is lower than the level of the sample solution, then the sample will be pushed into the diaphragm by the hydrostatic pressure, and then contaminate, or in the worst case, it will block it. And of course, is the selected steering equipment suitable for the desired application? Does the stirrer size correspond to the beaker dimensions? Does a magnetic stirrer provide sufficient steering, or would a propeller stirrer be much better? All these aspects should be part of a written standard operation procedure, or in short, the SOP, so that every user exactly knows what equipment to use and how to prepare it. In case the hardware check is okay, then reassure that the peripheral units are correctly assigned in the titration method, or have not been changed accidentally or exchanged physically. Are the burette and the titrant correct? Is the right electrode connected to the correct measuring interface? And is the steering speed adjusted correctly? The steering settings are very important, and special care has to be taken when stirrers with manual steering speed adjustments are used. Also here, the steering speed could have been changed accidentally, and this was not recognized before the titration has been started. The use of modern intelligent titration equipment can reduce this daily effort almost to zero. What are the advantages? Intelligent electrodes and dosing burettes have all important data like electrode type, calibration data, titrant solution, and concentration stored on a memory chip, which allows automatic recognition once the electrode or a burette is connected to the titrator. This avoids typing errors during configuration and, of course, simplifies the exchange or replacement of such devices. In addition, the user can define monitoring intervals to remind the user on recalibration of the electrode or revalidation of the titer value, or simply block the instrument in case any of these intervals have expired. The use of such units can also be locked in the titration method, means the application cannot be carried out when the correct electrode or burette is not corrected. When also the stirrer is controlled by the instrument or software, then all important parts of the titration systems are fully traceable and every action is documented in the determination file. Completely independent from the titration instrument, but absolutely of the same importance, is the sample preparation. Are solid samples really always homogenized sufficiently? And also how much time and other lab equipment is required for this? How much time do you spend cleaning this equipment? Has the sample really been filtrated quantitatively? And how can you verify this? Does the liquid handling or sampling have the required accuracy and reproducibility? And last but not least, what about your weighing? Is the sample weight manually transferred to the instrument, or is the balance directly connected to the titrator? And most important for all different steps, what happens if different users are doing exactly the same per sample preparation? Does every user really do exactly the same? Most of the mentioned sample preparation procedures can be fully automated. This includes simple addition of auxiliary reagents or solvents up to the homogenization of solid samples or automatic pipetting of liquid samples. Only this ensures that a sample preparation step is done exactly the same way for each single determination. It also makes it fully traceable, since everything is a part of the titration method and therefore documented in the software. By using automation, you make the analysis fully independent of the skills of the application chemist. A good example for this is the titration of chloride in solid samples. This could be, for example, a food sample like cheese or meat, or let's say, any pharmaceutical sample. So how is this then done? First of all, the sample is weighed into the titration beaker and placed on the sample processor. Then, already as part of the automated procedure, the required solvent is added. Once this is done, the homogenization with the amounts of homogenizer is started at very high speed. After this, the required nitric acid is added, and finally, the sample solution is then titrated with silver nitrate by using the homogenizer as stirrer, of course, and at reduced speed. Once the titration is finished, the electrode and homogenizer are automatically rinsed, and the system is ready for the next sample to be done. And the user? He only had to ensure that the sample is correctly weighed into the titration beaker and correctly placed on the sample processor. So next to the equipment and to the sample preparation, what else could be a reason for a wrong or invalid result? The result usually is calculated using the calculation formula in the instrument, so maybe it is worth checking this first. Check if the calculation formula has been entered correctly, and also that all required variables are available. So therefore you may reconfirm the following. Are titrant concentration and titer value correct? Has the stoichiometry and the factor of the chemical reaction been considered? What about the sample size? Has it been entered correctly? Or entered at all? And has an equivalence point been detected? And if so, is it the correct one? If no equivalence point could be found, then you first should check the titration curve. If the curve shows an immediate potential drop right after the beginning, then usually either the sample size is too low or the titrant concentration is too high. If it is vice versa, means there is no significant signal change for a long time, then this is either too much sample, the titrant concentration is too low, or the titration has stopped too early, maybe because the parameter stop volume is too low. If there is no curve at all, but only more or less a straight line, then you should check the titration hardware. Is the sensor connected to the correct measuring interface? Is the sensor working at all? Is the titrant bottle already empty, or is the bullet tip really pointing into the titration vessel? So there are many reasons that could be a cause for an effect like this. But also, if there is no endpoint at the expected volume, then an unstable measuring signal could be the cause for this. In case there is an unexpected peak in the titration curve, this peak could be recognized as equivalence point if no further precautions are taken. Such peaks may be caused by electrostatic effects, or if the instrument is manipulated during the course of the titration. If the titration curve or the measuring point list is not recorded during titration, it is almost impossible to identify such peaks and to re-evaluate the titration. If you are facing such peaks, but the measured potential at the approximate volume of the equivalence point is known, then evaluation windows could be defined. In this case, only an equivalence point that is within these windows is considered, and any other spikes are ignored. Another reason for suddenly missing equivalence points could be based on the electrode. The response time of the electrode should always be fast enough for the titration, but usually this response time is increasing the older the electrode is, also for pH electrodes. The first indication for this is the titration duration. Even though the results are still good and the titration curves look perfect, the titration duration is getting longer. Once the electrode is getting too slow, and this is not compensated by adjusting the titration parameters, then it will happen that the titration results are getting higher since the sample is over-titrated. This normally cannot be seen in a single titration curve, but a curve overlay shows the slow shift of the titration curves. And looking at the endpoint recognition criteria, you can see that the peaks are getting wider, and more important, that the values are decreasing. If the value is then lower than the defined endpoint recognition criteria, then suddenly no equivalent point is found anymore, even though the titration curve itself still looks okay. This effect can also be seen for polymer membrane electrodes like the calcium ISC. The expected lifetime of such an electrode is usually up to 1 year, and the difference in performance can be seen in the following example, which is the titration of calcium, magnesium, and drinking water. The new electrode enables a clear separation of the calcium and the magnesium. The ERC has 2 clear peaks, especially for the magnesium. With little more than 3 minutes, the total titration duration is also reasonably fast. However, this changes with time. Again, the first indication, we're not looking at further titration details, is that the titration duration takes longer. The titration curve then shows all the details. The overall response of the sensor has decreased, the potential jumps have become much smaller, and the second equivalence point to indicate the magnesium, which is more or less very sharp for the new electrode, has almost disappeared. This may result in an either missing equivalence point for the magnesium, or the reproducibility of it is getting poor. So, as you can see, suddenly missing equivalent points are usually easy to explain when looking at the titration curve or a curve overlay. So an instrument or a titration software that enables this can be very helpful. In addition, I hope you have also seen that in suddenly missing equivalent points not necessarily is the fault of the instrument itself. Very often, other processes or consumables are responsible for this. This could be, in particular, an inadequate dosing rate in case the sensor has become too slow, or contamination of the sensor, usually a consequence of insufficient cleaning procedures. Last but not least, insufficient stirring can contribute when either the stirring speed has been modified or beaker or stirrer size has been changed. I already mentioned earlier, the importance of stirring is very often underestimated. This can also be seen in an example of surfactant titration. Here stirring becomes crucial, especially when the titration has reached the region of the equivalence point. If stirring is too weak, then the reaction between the sample analyte is not supported, which results in an unstable measuring signal. For this reason, a proper stirrer had to be used. In case a magnetic stirrer is used, beaker size and the size of the magnetic stirring bar should also be proportional. If proper stirring equipment is used, then the stirring efficiency is much better and the titration can be done without any issues. The titration curve is then very smooth, also in the region of the potential jump, much more precise and reproducible as the titration in the left picture. How about cleaning a sensor? How can I see that my cleaning or rinsing procedure is not sufficient and the stirrer is contaminated? Again, looking at a single titration or result will not necessarily provide the helpful information. In most cases, when a contaminated sensor is used, the instrument will still provide on the first view reasonable titration curve and a result. The users usually only get suspicious when the result is not what it should be. Again, a comparison of several titrations in a curve overlay may help, like this example from a non-aqueous titration of the acid number of used engine oil. These samples are very sticky, contaminated with black carbon or other solid particles. You see a real pain for any pH glass electrode. The increasing contamination of the electrode can immediately be detected when looking at the curve overlay of several samples with the same sample size. Each single curve still looks more or less reasonable, but first of all the equivalent points are shifted to higher values, and a much better sign for insufficient cleaning, the start potential of the titrations is varying significantly. Since always the same sample size is used, this should definitely not be the case. Looking at the sensor after these 5 titrations, we immediately see the problem. The sensor is covered with the sample, especially the glass membrane and the diaphragm. This increases the response time so that all consecutive titrations are over-titrated. Means you get too high results. If the sample is always the same, or if you have at least know the expected equivalence points, then you could react fast, either by improving your rinsing procedure. But what if the equivalence point is completely unknown? How can you guess that the found equivalence point is really correct? So either you rely on your rinsing procedures, or you have a fixed maintenance plan for your sensor, or you validate your titration system from time to time. Or, as an alternative, you may also look at an alternative titration technique that is not sensitive to contamination. This is the case for thermometric titration. I will not go into further details of this technique in this presentation, but thermometric titration is using the change in temperature in the sample solution that is caused by the reaction enthalpy of analyte and titrant. The sensor is a thermistor that has no chemical interaction with the sample solution and measures the chemical parameter, the temperature. This makes the method almost insensitive to any contamination, and therefore it provides much more reliable and reproducible results, as you can see in the graph, which is the same sample as before that could not be titrated properly with a pH glass electrode. Varying start potential for identical samples may not only be caused by a contaminated sensor. The sample solution itself may also contribute to this. This is especially the case for indirect titration methods or whenever a start volume is used. In such cases, the sample solution needs some time for the reaction of the analyte and the reagent. If the titration is started immediately after reagent addition, then the reaction may not yet be fully quantitative, which may result in an unstable reading after the first titrant additions. In worst case, if no further precautions are taken in the titration method, One of these peaks is evaluated as equivalence point, and the titration is stopped much too early with wrong results. This can be solved by allowing a certain waiting time or pause before the titration begins. The sample solution and the sensor have sufficient time to stabilize, which provides a smooth titration curve and a reliable titration, as you can see in this example for the green titration curve. So, most of the titration examples we have seen so far have shown any significant change of the titration curve. But what to do if the shape of the titration curve is not changing at all, but the titration results are still not good or are not what they should be? Either the result is wrong or you see a steady shift, especially to higher values. In this case, you should first check the reagents and maybe your weighing procedure. Is the sample size really correct, or has it correctly been transferred from the balance to the instruments? Nowadays, many lab balancers can send the sample weight directly to the titrator or the titration software, so typing errors can be completely avoided. But also the titrant might be responsible for this. As mentioned earlier, sodium hydroxide or iodine solutions require regular titer determination to compensate the degradation caused by either carbon dioxide uptake or oxidation or reduction. If this is not done, the real concentration is reduced and more titrant is required for each consecutive titration. The titration curve will look absolutely the same in such cases. So, if you are not checking your titration setup frequently, or you're doing a linearity check of your titration result, you may not even recognize this shift of the equivalence points. Another typical application problem are air bubbles in the burette or in this tubing. All titrations are good, except one outlier with one strange bend in the titration curve that causes a shift and a wrong result. This is a typical indication for an air bubble in the titration tubing. Air instead of titrant is dosed for one or more volume increments, so there's a shift of the measuring signal on the volume axis. Air bubbles are something that should usually be checked during the preparation of the titration hardware, but sometimes they may also be formed during the use of the titration equipment. The question is, how can you avoid this? First of all, you should work with degassed titrants whenever possible. In addition, whenever non-aqueous titrants are used, check whether they are suitable for maximum dosing rates. This is of special importance for refilling the burette. Solvents like methanol or acetone may evaporate, caused by the underpressure generated during aspiration. So please regularly check the glass cylinder for air bubbles, especially when a classical exchange unit type burette is used. In case there is an air bubble in the glass cylinder, it will automatically be dosed through the tubing since the piston is moving upwards. Also check the tubing connections, whether they are still tight. The connections may be untight, not only when they are connected too loose. Also, too much force applied during connection may deform the tubing and cause a leak. But also the titrants might contribute to air bubbles. This might happen when corrosive reagents like concentrated alkaline solutions or reagents like iodine or permanganate, which tend to crystallization, are used. In both cases, the sealing lips of the piston might be scratched if crystals are formed, which results in a damage of the glass cylinder. Therefore, regular maintenance and replacement of such units is recommended, especially when such reagents are used. Air bubbles in dosing tubings can also be avoided by using a different burette type, the Docino technology. Here the burette motor is on top of the dosing cylinder, means the piston is moving downwards. Any small air bubble that might be generated in the glass cylinder is then trapped and not dosed through the tubing. In addition, thanks to the design of the piston and glass cylinder, there is no dead volume in the burette anymore. This allows a fully automatic preparation procedure that can be programmed as an initial start sequence. This ensures that the burette is prepared all time exactly the same way, and any air bubble is is removed automatically. So, enough about titration problems. Please let me continue with some remarks on how to improve titration performance. One major issue in titration troubleshooting is how to improve the separation of more than one endpoint in a titration. This might be the case whenever two different species are to be determined. And again, a very typical example is the titration of calcium-magnesium in water samples. Whenever the molar ratio of both is reasonable, then there is a good separation of both endpoints. But what if one species concentration is much higher than the other? In such cases, the separation of both equivalence points might not be as easy, and therefore also not reproducible anymore. In this case, spiking with a known amount of the lower concentrated species can help. The two equivalent points can then be separated much better, but of course, the addition of the spiking solution has to be very precise and reproducible as well. In aqueous acid-base titrations, the separation of acid mixtures is a common challenge. If a mixture of hydrochloric and sulfuric acid is titrated in water as solvent, then only one equivalence point is obtained since the pK values of all protons are too close. The specification of hydrochloric and sulfuric acid would require a second titration, either to determine the chloride or sulfate content. However, this might be avoided by adding acetone as solvent. In this case, the pK values of the sulfuric acid are shifted, and the titration now provides two equivalent points. The first corresponds to the HCl and the first proton of the sulfuric acid, the second equivalence point only to the second proton of the sulfuric acid. The specific acid concentrations can then be calculated out of the difference of the two equivalence points. But sometimes not even the use of organic solvents is necessary. For example, also the addition of a salt like sodium chloride will improve performance. This can be shown by this example, titration of phosphoric acid. The blue titration curve is a regular titration with water as solvent and no addition of sodium chloride. As expected for this, you can identify the equivalence points for the first and second proton. By adding sodium chloride, the pK value of the third proton is then shifted and then can be detected. As you can see from the volumes of the equivalence points, the addition of the sodium chloride has no influence on the accuracy of the titration. The values are really identical. Last but not least, since every lab nowadays is forced to be as efficient as possible, how can you optimize the titrations to be faster and more cost efficient? First of all, everybody wants to be faster. In a titration, usually only the result means the recognition of the equivalence point is of interest. So why not simply cutting off unnecessary parts of a titration? If the range of the equivalence point is known, which is very often the case for routine titrations in quality control, you can simply use a start volume that will be added at the start of the titration sequence. Important is only that this is part of the specific titration command and not a separate dosing step. Otherwise it might not be considered for the final volume of the equivalence point. The start volume reduces the titration time significantly and can be selected either as fixed volume or be calculated live as relative start volume for each individual sample size. When to stop a titration? In many cases, the titrations are done to a fixed stop volume, very often even the bullet volume. This means that usually titrant is wasted. The better option is to use the function stop after equivalence point, which means the titration is stopped immediately after the equivalence point has been detected. This ensures that only the minimum amount of titrant is consumed. But please be aware that this only may work for stable and reproducible titrations. In case there is the risk that wrong equivalence points are recognized, the stop after EP might provide wrong results. In case you have titrations with more than one equivalence point, then this parameter can also be adjusted and be set to stop after the second, third, or whatever equivalence point. The advantage of both start volume and stop after EP is that the titration result itself is not affected. This neither has an influence on the precision nor on the reproducibility of your titrations. Another tool to reduce the titration duration is to force a faster addition of volume increments, means the modification of the titration parameters. This is usually done by increasing the signal drift criteria to faster additions, or modification of the maximum or minimum volume increment to have less titrant additions. However, as this example of the calcium-magnesium titration shows, the signal drift criteria can only be increased until the accuracy is not affected. In the end, you have to consider that the modification of these parameters, the signal drift or the minimum maximum volume increment, may affect both the correctness of the titration and the reproducibility in case of several titrations. Correctness, since the titrations might become too fast and generate too high results, or poor reproducibility due to a low number of measuring points. But in general, if proper values are chosen for both, you can have good tools to improve the titration performance. The same applies for titrations with fixed endpoints. The dynamic range, the stop drift, and the minimum titration rate in the dynamic range are the most important parameters to define the titration duration and precision. Choosing a large value for the minimum titration rate usually gives fast titration, but then there's also the risk of over-titration in case the value is way too large. Smaller values provide the precision, but lead to much longer titration durations. So in the end, it is up to the user to find the right balance between speed and precision. Next to faster additions, also the reagent consumption has to be considered. Not only the costs of the reagents are significant, nowadays also the disposal or the recycling has to be considered. Therefore, it is worth thinking on how these costs can be reduced. The earlier shown parameter stop after EP is one option to save titrant solution, but you may in general ask yourself what other reagents could be reduced. Many written titration procedures have a historical development, and the recommended sample and beaker sizes, as well as the solvent volumes, have just been copied. In addition, the amount of solvent is usually chosen to fully immerse the sensor. But maybe there are already smaller electrodes available that allow the reduction of the solvent. And you should also check whether the titration could be done with less sample, because very often the specified amount of solvent is required to dissolve a specified sample size. I know everybody thinks never change a running system, and you immediately also think that changing any parameter in an existing SOP may require revalidation of the method. But in the end, this could pay off very fast. Usually, the amount of solvent has no influence on the titration result. Means you really should ask yourself whether the titration can be done with less solvent in a smaller beaker, or maybe in an optimized or smaller titration vessel, like so-called micro-titration vessels. Here, with the dedicated design, the use of less solvent is supported. So, at this point, I've already reached the end of my presentation. So please allow me a short summary on troubleshooting in titration. Before you start your daily work with the instrument, allow yourself a few minutes to check the instrument hardware and peripheral units. These few minutes can save hours of troubleshooting later on. Also check the reagents for their validity. The use of intelligent electrodes and dosing burets minimizes this effort almost to zero, and immediately informs the user and forces him to solve the problem. Ensure that your sample preparation is really reproducible. Very often automation is not considered for financial reasons. But if you calculate the real costs for manual sample preparation, then an automated system pays off very fast. Less interaction with the instrument, less errors, and of course, much better documentation. The titration parameters have to be adjusted to the chemical reaction in the titration vessel and the sensor condition. Either make sure that all sensors are in good condition or adjust this by changing the titration parameters. The rinsing procedure for the sensor or titration setup has the same importance as any other step in the titration. Therefore, make sure it is part of your SOP. And last but not least, a single titration is not always sufficient to solve a titration issue. Very often, several titrations have to be compared to find a solution. As a final summary, I dare to say, in most cases, not the titration method itself causes the problem already existed before the start button on the titrator was pressed. So thank you very much for your attention. Following on this presentation, you're welcome to share feedback or answer questions. However, please understand that we cannot handle individual titration issues here in this discussion session. But you are more than invited to write your issue and we'll follow up later on. So thanks again for joining. Bye.